Hi, welcome back to Statics 1. Today we're going to be talking about free body diagrams. I think we mentioned that last time. We're going to go a little bit deeper into it and look at the different types of supports and how they relate to the drawing the free body diagram. So let me kind of first introduce the basic concept. Since the beginning of the term we've been doing problems like, a typical one was like at the beginning, you remember, we had like a hook eye or something like that, and we said things like, okay, we have these imposed forces. This is, let's say this one's 100 pounds, and this one is like 70 pounds. And we would say something like, well, what is the resultant vector? And we know we can use the parallelogram law to figure out what that resultant vector is. Something out here. And that was fine and good, and that was useful. But we never really considered what's going on at the support itself. So that's what we're going to get at. So what we're going to do in this case, we're going to take that support and we're going to basically separate it from our system. So it's still here. Here's the support. And there's going to be a force, essentially. And obviously from Newton's law, we know that forces are always going to be equal and opposite. So our support is essentially restraining the movement by opposing a force in this direction, and our body here, and essentially these forces, are applying a force on the support itself. So those are the kind of things we're going to do, and this is essentially the essence of what a free body diagram is. So we're essentially separating it from the supports, and we're going to include explicitly a description of those forces. Time out while I answer my phone. The nature of these support reactions varies depending on the type of support, and that's what I want to talk about a little bit. So for example, if this were a cable, this would be entirely appropriate. If there was a cable between here and here, that would be entirely appropriate support reaction, because the support could only go in the direction that you're pulling the cable. Although there might be like an angle of departure. If these were pulling up this way, we might find that it forms some angle theta. However, if this were a fixed support, imagine this was a screw eye that you screwed into this wall over here, that's going to impose an entirely different set of forces. So for example, in addition to holding it next to the wall, it's also applying a moment. And I'll draw the moment in a positive direction. And on this side we have essentially counter acting moment, because Newton's laws, of course. And it's also preventing the vertical translation of this thing. So there would be a force, and I'll draw it this way. And on this side, essentially we have a counter-acting force. So we have no unbalanced forces, right? That's the key. So now we could evaluate this whole system by itself and solve for these three moments, knowing that this is a rigid body and that it's not moving. Okay, so that's where we're going at with the free body diagrams. There's essentially, it can be done this is a very simple system, obviously, but imagine you have a truss, which we're going to be looking at a lot. So a truss would be, typically it's a set of triangular elements. You see a triangle here, triangle, 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 and there'll be supports here. In fact, what I'll do is I'll draw first the essentially the entire structure. So we have a hinge on that side, roller on that side. We haven't really talked about why we're like that. But imagine someone says, draw me a free body diagram of the entire structure. We would just essentially draw the outline, because we wouldn't really care about all the details inside the system. Oh, and there probably would be some loads associated with this. So we might have a load here, and a load here. Okay, so if we're going to draw a free body diagram, instead of representing the visually the supports, our hinge and our roller, we're going to show the reaction, the support reactions imposed by these. So a hinge prevents translation in the horizontal and the vertical direction. So it actually has a force laterally, horizontally, and vertically. But because it's a hinge, right, it allows rotation. So it's not, there's no moment force applied at that location. At this end, we have a roller. So we have a roller would imply essentially only a vertical force, but it would not prevent translation horizontally in the x direction. So the support reaction would only be a vertical. And then to complete the free body diagram, we have, of course, to include our original loads. These are the 3 loads here. So this is essentially our free body diagram. We would also put in, I'll actually go kind of how we designate the points and how we actually solve for. But the goal, and typically in this kind of situation where someone says, draw the free body diagram, and then solve for the support reaction. So we'd solve for that reaction, that reaction, that reaction, for known loads, because the loads are essentially going to be specified depending on the physical system that you're operating on. On the other hand, someone might say, what is the free body diagram for this member here? So you'd actually could break that member out, and we could draw a free body diagram for just that member. So it's going to also have free body diagram. So here you draw essentially the member, and it'll have forces applied to it as well. In this case, we have, these are pin supports. So there's no moment applied to these. And typically with a truss, at least they're represented as being pin supports. So this will have a force horizontally, vertically, and then that would be essentially on both ends. Okay, that's how you'd represent the free body diagram for this member that essentially we've isolated from the system. Okay, and then we could do that for every one of these, and we could then solve for all the support reactions. And we're going to actually do that, and that's one of the goals in the next day, in a week or two. We're going to get there. All right, so what I want to do now is to talk a bit about the types of supports that you're typically going to see and the types of forces. And there is a table in the text. It's actually table 4-1 in the textbook that we're using. And I'm going to show you sort of the 3 most common, which are a hinge, a roller, and then a fixed support. And then we'll talk about a few of the other ones, a cable and some other types. But you can always refer back to the table if you're confused about the types of forces that are being applied. Okay, let's start. Let's just come over here. So, in this case, let me see how they. So it could be called either a pin or a hinge. This would be a pin or a hinge. And actually, the way we're going to talk about it today is we're going to represent purely on 2D, but there are essentially 3D analogs for every one of these types of support. So these are support types, and you can imagine, let me draw it like this, and I'll draw it kind of typically how, there's a number of ways they're drawn, but sometimes you'll see it like that. So essentially it's fixed to this surface, it's basically bolted down or whatever, and then you have some member here, and then it's this pin essentially passes through the bracket and this support member. And the type of forces that will be applied, so if we were to draw a free body diagram of this, we have a force in this direction and a force in that direction. All right, so that is our first one, the pin or hinge. Now let's talk about a roller. And actually, there's 2 support types that have essentially the same support reactions. So I'll kind of lump them together. Well, actually, let's start with just a roller by itself, and then we'll talk about the other one. So a roller is typically represented in 2 ways. Sometimes you'll see it like that, and so that would be like a hinge on top of this roller. You can see that essentially just think of this as being, it's fixed here, but the hinge itself is allowed to move. The other way you'll see it frequently represented as a circle like that. And in either case, you'll have a something fixed to it, or you may have a member like that fixed to it. And the free body diagram for the member with that type of a support would look like something like you'd have a force only in the vertical direction. Okay, so either one of these would impose a force in a vertical direction. Now actually you could have a roller which is on a slanted surface like this, and again like that. Then we draw our hinge here like this, and I'm going to draw my member, and I'll just draw the kind of short member. So here's a roller on a slanted surface, and in this case the force is going to be perpendicular to that surface. So it'll have something like this. So you have a force, and it's essentially restraining motion perpendicular to this surface, but allowing motion parallel to that surface. So here's the sort of classical ones: pin and hinge, roller, and there's a third one, a rocker, which essentially has the same impact as a roller. So if you see one in a drawing, and it looks something like that, and you can imagine this thing is being allowed to sort of rock either way. And if we were to draw a member attached to it, so again we have a pin through this thing holding our member to our rocker, and this is allowing motion in the direction parallel to our surface, but providing a support reaction that's holding it perpendicular to our surface. So if I drew the free body diagram for it, it would look something like this, and we'd have a vertical force. So here's my diagram or sketch of the rocker attached to a member, and here's the free body diagram for this member, which is the member with a force in the vertical direction, which is perpendicular to our surface that the rocker would be attached to. So this is called a rocker. And so you can see the free body diagram for a rocker is essentially equivalent to the free body diagram for a roller, which is why I kind of lumped the two together. There's one third kind that we'll talk about, and then if there are any other types of supports, you should be able to look them up and learn more about them yourself. But the other one, and this is kind of what we're looking at here, it's called a fixed support. Okay, and a fixed support would be a situation where you have something like this, and this would be like a cantilever situation, right? You have no support for this thing down at this end, but somehow this thing is holding this up because this is bolted in. And you could imagine that you have like a bracket or something in here, or maybe this is actually screwed into the wall. And the free body diagram for this is going to actually have three forces. It'll have one force, and I'll draw that now. So I'm going to draw, this is just the member. We're going to draw a free body diagram for this member. They have a vertical force, a horizontal force, and in this case they'll have a moment. Okay, and it sort of makes sense because this thing, if you had, for example, a force at that end, in order for you to hold this thing up, you have to be, at this end, if you think of yourself as holding this thing, right, it's going to want to rotate this way. So you're going to be pushing back to cause it to not rotate, and that's what that moment does. And that's why we need three supports. So this one actually has three support reactions, or three forces providing support. The pin or hinge has two, and our roller or rocker only has one force. Okay, so that's basically a pretty quick overview of free body diagrams and our support reactions of three sort of classical support types in 2D. So these are for coplanar problems, which are very useful for dealing with problems like this, which are trusses. And we're going to be talking about a lot about trusses coming in the coming weeks. So the next thing we're going to do is do some examples where we actually solve for these support reactions. And so that's what we're going to do next. So if you have any questions, send me an email. Otherwise, I'll see you in class.